So, where are the robots? We have been told for 40 years already that they are coming. Very soon, they will be doing everything for us. They will be cooking, cleaning, buying things, shopping, building. But they aren't here. So, what can we do about that? I want to give a little bit of different perspective of how we can perhaps look at these intelligent machines at a different way. When I was young, I asked myself, what's the most interesting thing in the universe? And my answer was the brain. A human brain, and of course, human brain defines us as a species. That what makes us unique, our intelligence, everything we have ever created, this building, computer software, you name it, has been a product of our brain. But as far as I know, as far as we know, it the only thing in the universe actually knows about the universe as a whole. It's the only thing that can ask questions about things that are far in the future, the past, very large. In fact, it is the creation of knowledge, and without brain, knowledge would not exist. So I set out to think this is a good thing to study. So I set out two goals. The first goal was work on discovering the neural coding to understand and uncover fundamental principles governing how the brain processes information to drive perception, behavior, and other functions. We are taking a systematic approach to understand how information is encoded and decoded in the human brain. Then I said, once we figure this out, we should be able to build machines on those principles, and this could be fantastic machines. This is not about building, the human-like robot, just building machines to learn like human brain, and we build fantastic tools for humanity. We have been pursuing these goals now over the last years through several approaches, visual cognition, memory system, and so on. And one thing we do called saliency-based visual attention model. Here, I want to present a brief overview of our model for the bottom-up control of visual attention in primates. Given an input image, this system attempts to predict which location in the image will automatically and unconsciously draw attention towards them. In this biologically inspired system, an input image is decomposed into a set of multi-scale neutral feature maps, which extract local spectral discontinuity in the modalities of color, intensity, and orientation. Each feature map is endowed with nonlinear spectrally competitive dynamics, so that the response of a neuron at a given location in the map is modulated by the activity in the neighboring neurons. Textual modulation, also inspired from recent neurobiological findings, has proven remarkably efficient at extracting salient targets from the cluttered backgrounds. All the feature maps are then combined into a unique scalar saliency map, which encodes for the salience of the location in the scene, irrespectively of the particular feature which detected this location as conspicuous. A winner-take-all neural network then detects the point of the highest salience in the map at any given time and draws the focus of attention towards this location. In order to allow the focus of attention to shift to the next most salient target, the currently attended target is transiently inhabited in the saliency map. This is another mechanism inhabitation of return, which has been intensively studied in the human psychophysics. The interplay between winner-take-all and inhabitation of return ensures that the saliency map is scanned in order of decreasing saliency by the focus of attention, and generates the model output in the form of spatio-temporal attentional scan paths. Recently, we have applied this model to many different visual tasks using static images, including a member of ATR task where we observed remarkable model performance at picking out salient targets from cluttered environments. This includes the reproduction by the model of human behavior in classical visual search tasks. A demonstration of very strong robustness of saliency computation with respect to image noise, the automatic detection of traffic signs and other salient objects in the nature environment, the detection of pedestrians in the nature signs, the evaluation of advertising signs, and the detection of military vehicles in cluttered rural environments. The model is developed in accordance with the known autonomy and physiology of the visual system of a macaque monkey. It comprises two interacting stages. A first, parallel pretentative extraction of visual features across 50 spectral maps for orientation, intensity, and color at 6 spectral scales. The features are computed using linear filtering and central surrounded structures, similar to those found experimentally in visual receptive fields. A slow and sequential focal attention shifting mechanism, using a winner-take-all neural network to select the most conspicuous image location, and a habitation of return mechanism to generate attentional shifts. The link between two stages is the saliency map, which typographically encodes for the local conspicuity in the visual sign, and controls where the focus of attention is currently deployed. The saliency map directly receives its input from the pre-attentative parallel feature extraction stage. Supervised learning can be introduced to bias the relative weights of the features in the construction of saliency map and achieve some degrees of specialization towards target detection tasks. And you can extend it more research way towards robotics and vision. There is a lot of other science tools documentations have to be done. Well, from what I see, it sounds simple, but there is a lot we don't know about visual system. But we also made a lot of progress. I feel it's like we are in the 1950s in the computing era. In 1950, we just started building computers, and they are just become partially valuable and interesting. But we still have decades of research to go to where we are today and we are right now. And finally, this stuff is really important. I can't think of anything more important work in my life. That is why I done this. And I know some people in this room hopefully feel the same way. It's important because working build amazing tools for humanity, and we can build machines that are smarter, faster, navigate, and help us and make our world better. It's the only way I think actually gonna help us explore the universe and to get out there actually physically explore the interest. But also help us to think about the problems we struggled as we have today as a human, so this is a tool for humanity. I think it's gonna be as important as computing, and I hope a few if you are interested in and check it out. Thank you very much.